In this video, we're going to calculate the probabilities of type 1 and type 2 errors for an upper tail binomial distribution hypothesis test using a TI-Nspire calculator. So just a quick review. A type 1 error is when you reject the null hypothesis when it's true because your sample fell into the critical region. A type 2 error is when you keep the null hypothesis when it's false because your sample fell into the acceptance region even though the alternate hypothesis is true. In a previous video, I talked about the normal distribution, so for Z or T tests, and that the probability of a type 1 error equals the probability that your sample fell in the acceptance region, given that, the null hypothesis is true. And this ends up equaling, this probability ends up equaling the alpha. That is not the case for binomial and Poisson. It's not perfectly alpha, and that is because your if you have if you're using a level of significance at 5%, that may not actually fall on some fixed value that you would really get. This might be like 3% and this might be 7%. And that means you're not really using an alpha of 5%. And that means that your probability of a type 1 is not actually your alpha. It's going to be whatever your critical value is. So the probability of a type 1 error for a binomial distribution is the probability of your sample falling in the critical region, even though your null hypothesis claim for the proportion of success is true. And that means that we need to actually figure out what the critical region is, and we're going to use that for our upper and lower bounds in the calculation. In order to figure out this critical region, we first need to define a function in a calculator page. Then we're going to open a spreadsheet and turn it into a table. And I will show you how to do that later on. But so let's say you've used that to figure out your critical region. If you have a lower tail test, your critical value will be over here. And if you have an upper tail test, your critical value will be over here. So then when you're calculating the probability of a type 1 error over here, you're going to enter your sample size n. You're going to enter the null hypothesis claim for the proportion of success. Your critical region, if you're doing a lower tail test, would be 0 up to your critical value. If you're doing an upper tail test, then, this guy here, then your critical region is that critical value up to n, which is your sample size, okay? Then, to calculate the probability of a type 2 error, we want to find the probability that your sample fell in the acceptance region, given that a different proportion of success is true, not the claim. So they have to, in IB math, they're going to tell you this value. It will be given, the true value will be given in the problem. Okay, that's just for IB math. I don't know what AP Stats does or college stats. So they'll say, well, the true value, unbeknownst to you or after further testing, came out to something different than what you thought. Find the probability of a type 2 error. And so we are going to be calculating the probability your sample falls in the acceptance region right here. And that will be your upper and lower tail bound. You will still use your sample size for n, and then you will use the given alternate hypothesis proportion of success that's given in the problem. You'll enter that there. If you have a lower tail for your critical region, which meant you went 0 up to a critical value here, that means your acceptance region is going to be the opposite side, so critical value up to n. However, if you're doing an upper tail test, then your acceptance region is on the left. And so we'd switch these around. Your critical value, your critical region will be CV up to N, and your acceptance region would be 0 up to CV, the critical value. So let's do an example. Okay, you planted 30 flowers, and to protect them, you purchased a a natural bug spray. The package claims that no more than 10% of flowers will react badly to the spray. Let X be your variable for the number of flowers that react badly to the spray. So that is your X-axis on the distribution there. And the level of significance you use is 5%. So your alpha is 0.05. The null hypothesis is that the proportion of success in this case is defined as flowers reacting badly, is going to be 10%. And the alternate hypothesis is what we're concerned about, more than 10% reacting badly. And so this is going to be an upper tail test, which we need to think about when we are setting up our bounds. The probability of a type 1 error means we need to find the probability that your sample fell in the critical region. So we need to find the critical region first. On a calculator page, which I'll show you in a second, we're going to define a function as a binomial CDF with n is your sample size, p is the claimed proportion of success. Our lower bound is going to be changing, so we'll call it x because anything that changes is a variable. We like to use x for variables. And our upper bound is our n. So what we're doing here is we are calculating all the different possible binomial PDFs or CDFs, for trying to figure out, well, where does 5% fall? Does 5% fall, at 29 or bigger? Or does it fall at 10 or bigger, or what? And so this table is going to calculate all the different binomial CDFs. And so we're checking at 30, then we check 29 or bigger, 28 or bigger, all the way down. And so since that lower bound is changing, that's why we're going to set X as your lower bound. You will then make a spreadsheet and convert it to a table. And so these are all the variable outcomes. And we did an upper tail, so this is outcomes, larger than or equal to these various numbers that we're calculating. And these are the p-values that go with each one. So we look for a p-value that is smaller than 5%. So right in the middle here is where 5% happens. And then anything bigger than that, these are number of flowers being, reacting badly. Anything bigger than that is going to be in the critical region. So 7 is your critical value, and 7 or bigger is your critical region. So I'm going to mark that here. 7 is critical value, and then critical region is X greater than or equal to 7 flowers reacting badly. And that means later that your acceptance region is going to be 6 or fewer flowers reacting badly, and that's your acceptance region. We'll use that for part B. Now that you know your critical region, we're going to calculate the probability that X fell in that critical region under the assumption or the condition that the null hypothesis is true. That's just a binomial CDF with your sample size n, your null proportion of success, your lower bound is 7, and your upper bound is n. That comes out to about 2.58%. If you want to make this value smaller, you would reduce the alpha. If you want to reduce the probability of a type 1 error, you reduce alpha. Well, alpha was already 5%, and this is smaller than 5% already. So you'd have to reduce alpha even more to say 1% or 0.1% maybe. That would reduce your probability of a type 1 error. In part B, unbeknownst to you, the true value of the proportion of success is 15%, not 10%. Find the probability of a type 2 error. So the probability of a type 2 error is the probability that your sample, how many flowers you counted out of 30, fell into the acceptance region. And our acceptance region was 6 or fewer. So that's the acceptance region right there. Given this null or this alternate hypothesis that P is actually bigger, and you have to be given this problem, this value in the problem. And so all we have to do is a binomial CDF. Sample size is still 30 flowers. The proportion of success is what the alternate was given, the true value. Then we're looking at lower bound is 0 and upper bound is 6, and that comes out to about 84.7%. So if the true value was actually 15%, then your probability of a type 2 error is actually fairly high, nearly 85%. And if you wanted to reduce the probability of a type 2 error in this situation, you would want to use a larger sample size, a larger number of flowers to count up. So now I'm going to show you how to do that on the calculator. In your TI-Nspire, we're going to start with a new document, and we want to choose a calculator. We cannot do this work in a scratch pad because we're going to need to add another page here with a spreadsheet on it. So start with a calculator, and we're going to type in F1 parentheses X, close parentheses, so that we can define a function. And to define the function, we're going to hit Control and the button next to the 9 right there, and it pops out together :=. That's the definition symbol. Go Menu, Probability or Stats, and choose Distributions. Then we want the binomial CDF. So we had 30 flowers, and the null hypothesis was 10%. We are doing an upper tail test here. So we want the lower bound to be X, and we're going to be checking all the upper tails. So we're going to check 30. That'll be a binomial PDF. Then we'll have 29 to 30. Then we'll do 28 to 30, 27 to 30, and it's going to create a whole list of different binomial CDFs. And that way we can then look through the list and see where does 5% fall? Where does our alpha fall? So once you see the word done, we're going to add a page. So hit Control Doc, and that will give you the option to add a page. We're going to choose number 4, spreadsheet. And we're now going to turn the spreadsheet into a table by doing Control T. And you can see that we have our defined function there. I'm going to hit Enter, and it autofills. So these are all the possible X outcomes. So for 1 or more flowers, you can see the p-value, the probability of 1 or more flowers having an issue would be 95.8%. Let's keep going down the list until we see smaller than 5%, and there it is. So this is smaller than 5%, and then it gets smaller still because it's an upper tail. So that means 7 is my critical value. My critical region is 7 or bigger, and my acceptance region is 6 or fewer flowers having a bad reaction. Okay, so now I know my critical region is 7 or more. I'm going to go back to my calculator page, and I'm going to do a binomial CDF to calculate the probability of a type 1 error. So probability or stats, choose distributions. Letter B is binomial CDF. So 30 flowers. The null hypothesis is what's used for calculating a type 1 error. And we're finding the probability of being in the critical region. So the critical region was 7 or more. And the most flowers we have are 30. Hit OK, and there's your probability of a type 1 error. Then to calculate the probability of a type 2 error, we do the same steps. Letter B for binomial CDF, 30. But for probability of success or proportion of success, we're going to use the given alternate proportion of success, which was 15%. And then the acceptance region is on the lower side. So we're going to go 0 up to 6. That's my acceptance region. And there is the probability of a type 2 error.